Hey chemistry kids, so we're looking at the factors that can affect our enzymes. This varies all over a bit. It's a bit it varies a bit on how much detail they go into, so I'm trying to give you an overview of the detail. Make sure you are using your data book, because there's no way you could do some of this stuff without remembering. Make sure you go to that Jamie Kennedy website or blog or whatever it is, where he's shown you this stuff, and try to, rather than trying to remember the details of this, like what this, remember the colors, remember the sequence, remember this, rather than trying to work it out as you go. It's going to be much easier if you can kind of remember that than trying to remember all the data. I think it would be for me anyway. So we're looking at our factors that affect temperature, affect our enzymes. First one that I didn't really see in the book, but I think we should consider in terms of the general overview, is concentration. So the higher the concentration, the more reactants, the more enzymes there are to work with the reactants. So it's going to be much easier for all of those reactions to happen kind of in a timely manner. If there aren't many of them, it's not going to happen. And I think that's what happens with lactase. Your level of enzyme just goes, like, decreases. So I know that's definitely what happens with animals as you get older. So they have a lot of lactase to begin with when they are suckling, and then that level goes way, way down, and that's why they can't digest lactase anymore. They digest lactose anymore because they don't have the lactase. So that would be a very simple kind of thing to look at, how the concentration affects it. So that's where I would maybe start if I was looking at, that final question where it's like a student does this with that and the other. Make sure that concentration is the same across the board. There would be a point where it tops out, so no point adding more enzyme. Enzyme can be quite expensive. So that would be my first thing. That's a factor that affects how our enzymes work. Second one is temperature. So our bodies are around 37, some are slightly more, some are 37.5, 38. Everyone has a baseline, slightly different, but our enzymes are all going to work best at body temperature because that's what they're evolved to do. So that's where they're going to be working best. So if you were to design your experiment, you would have one at 37, and then you would go down and up from here. You could have some enzymes that are other temperature, so thermophilic bacteria. There's going to be super high temperatures. They're the ones we use for PCR. They go high, and they're what we're all evolved from. There'd be ones that go low. I don't know those off the top of my head, but we're looking at the human body, so we're going to be looking at these ones here. So why do we care? Well, the reason we care about this is because if you get too hot, so hyperthermia or hyperthermia, so too hot or too cold, the enzyme action slows way down because they're not working. So if it gets too hot, they can denature. If it gets too cold, their just reaction is not going to work quite so well. So what happens is we have our ideal temperature, which is about 37. So our enzymes are going to be at the top around here. Anything over this temperature, they're going to start to denature. So denaturing is where those bonds break, and this is going to be, it's going to vary depending on the structure, depending on where it is, what it does, but we're going to have a pretty strong drop off till they're not working anymore, and then they're not going to change shape, or they're not going to have any such issues. But as we get down cold, they're just not going to have the energy to get over that activation energy pump. So we need to make sure we're kind of within this ideal zone. So up here we got, maybe more up here, denature. And down here is just not enough energy. And both of those things are going to be bad for you. or whatever. I'm going to say bad for you. Right, so above the optimum, we've got this kinetic energy that's disrupting our structure. So our intermolecular bonds break up. So the secondary, tertiary and quaternary structure. So remember, it's still here because I don't tidy up often enough. I remember my protein. It's very beautiful. It's got some random thing affecting it. Remember my protein. As I start to give this energy, it starts to vibrate. As it starts to vibrate, all of these little hydrogen bonds, disulfide bonds, ionic, well, not the ionic bonds, all of these little bonds that are between this protein and this protein are going to start to break, and then this might float off. Then the active site has completely changed shape. So this is my enzyme here. This is gone. Well, that's a different shape now, so it's not going to react in the same way. My whatever is not going to fit in here as it did recently. Then what happens is if we keep giving it enough energy, it completely starts to denature and kind of untangle. Most of the time we're not going to give it enough energy to be broken our covalent bonds, so we're still going to end up with a big string of amino acids, but all of those intermolecular bonds that give it the secondary, tertiary and quaternary bonds are broke. If we do it mildly, so if we're just giving it a bit of heat and this is starting to come off and then we cool it down, that's fine, it's reversible. But if we give it too much heat, it's not reversible. So I put a picture of my pate. That was liver being denatured and cooked, so it was delicious. Making, cooking an egg, heating milk, you can't unheat it. Like you're breaking these proteins up and you're changing their structure, and they're not going to be able to go back. What do we use these for? So we're going to use it for things, well, for cooking is a big one. Our big brains have evolved because we cook food, and then we can get more energy from our food because we've cooked it before we've eaten it. And in the medical field, so you would heat or autoclave equipment before you use it in the lab, scalpels and test tubes and all that kind of stuff gets heated because that's going to break all of those bonds in my my bacteria, and I'm going to just end up with denatured proteins that really aren't going to do anything. They're just going to be there and it's not going to affect anything. So that's, I think, a pretty easy one to get your head around. The next one is pH. So pH is also denaturing. The amino acids are, I said, look at the Jamie Kennedy data book. Remember they've given you. So the thing to remember this is we have different pHs, different parts of the body. So your stomach is about pH 1.5 or 2. Your mouth is about 8, 7 and a bit. Your intestines are about 7. So different parts of your body have different pHs. So the proteins are going to be adapted to be in that environment. So we have our general structure of our amino acid here. And remember, amino acids are what are all building together to make our proteins. So we're just going to think of it as an individual amino acid to kind of simplify. So we have these slightly basic end and a slightly acidic end. And in normal conditions, these two are going to balance out. These two are balancing out to form a zwitterine. I think it's how you said. Right. So we've got a slightly positive end here. Slightly positive end here and a slightly negative end here. And overall, we've got no charge. So that's between 5 and 7 is we have this zwitterine. And we're not looking at the L group yet. We're just looking at our general structure. Then at a high pH, so when it's basic, we're getting this end here. I'm going to highlight it for you. So we've got this overall negative charge here. So that's what happened. Oh, if you can see, got that overall negative charge. And there's some good diagrams in, I think it's the Heinemann, gives you some good diagrams. Then at a low pH, when it's acidic, I should zoom into that a bit. There you go, that's going to make it easier. You end up with a positive charge on your nitrogen, which I didn't label because you've got that extra hydrogen joining here. So that's the very basics. And then we've got with our R groups. So we've got aspartic acid has got this acidic end here and this acidic end here. So if we put it into a basic solution, that's going to go and that's going to go, and we're going to end up with a 2+. Same with this one. Perhaps if I can do my negatives, 2 negatives, because this is going and that's going. Then if we have one of our basic ones, lysine, I think it's a good one. We've got this here and we've got this here, so those can both gain and gives us a 2+. So if this is in my acidic solution, it's going to have this structure. It's going to lose these and become, and it's going to gain, perhaps if I can talk, and become these pluses here and here, and that's going to affect everything. So think about, we've got this now here and here. That's going to affect our hydrogen bonding. It's going to affect our structure. And again, the same thing's going to happen with our temperature. We're going to have that disruption happening to all of those bonds in between. Again, no effect to the covalent bonding. We've still got that, but we've got the alpha helixes, the beta sheets, all of that into, area bonding, all of the quadratory structures. So when we have more than one, which is very common, that no longer is attracted to that. There's no intermolecular bonding, so it's going to be pulled off. So that's kind of the takeaway from that. Have a look at some questions. It's a bit of a remembering act, I think, rather than a deep dive in here. And it's going to be, if you've had a look at this guy's thing and had a look at this, it's going to help you a lot than trying to remember how to do it. Right, so have fun.